Great. Hi, everyone. Welcome to another online causal inference seminar. Today, we have the pleasure of welcoming Hyunseung Kang from University of Wisconsin-Madison, who will be talking about transfer learning between U.S. presidential elections. How much can we learn from a 2020 ad campaign to inform 2024 election? So very topical, given the year. He will have some help in the Q&A from one of his co-authors, Xinran Miao. So please do ask your questions there. And our discussant today will be Melody Huang from Harvard. So look forward to that conversation as well. Ying will be handling the questions today, so I'll switch over to her.
Thank you, Emma. Thank you, Emma. As usual, please submit your questions through the Q&A section. It's a button at the bottom of the Zoom window. Please submit it in the Q&A part instead of the chat for us to better track the questions. And I'll raise some of them to Hyunseung as he naturally stops. And otherwise, I believe Xinran will be answering them. Without further ado, please feel free to take over.
Can everyone see?
Yes, that looks great.
Great. Well, sorry. So I'll thank you for the invitation to the seminar. I was checking the last time I was here for a seminar. It was like the second week of when COVID lockdown happened. So this is a wonderful thing to be back, and it's actually highly relevant because we're going to be talking about how to learn from the past, specifically 2020, and how to inform that in the future decision in 2024. This is a joint work with my fantastic students, Xinran Miao, who will be handling questions, Jiwei from Biostat, and myself. And just before I begin, anything that's great about this, you should really contribute. You should really attribute it to Xinran, who's been really doing a lot of the data cleaning and also the development as well. And anything that's bad and wrong, you can all point that to me. So this is a one-slide review of overview of the talk. So the motivation for this entire talk is as follows: how much can you learn from a 2020 ad campaign that people ran to inform 2024 presidential ad campaigns coming up this election cycle? And the way we approach this question, answer this question, is actually using transfer learning. Apologize for the typo here, with sensitivity analysis. And there are two elements to this. The design elements are what is the study design that we're using? Essentially, we're going to allow for covariate shift, which effectively means that the voter demographics between 2020 and 2024 are allowed to be different. We're not going to assume that we measure the exact same thing in 2020 and 2024. We're not going to also assume that the ad effects are the same between 2020 and 2024. So we're going to make more or less realistic baselines to go through. The analysis elements are as follows. We're going to actually use a very simple design-inspired plugin estimator that's nonparametric and efficient. We're also going to propose a bootstrap approach that is theoretically correct in transfer learning. We do have, if time allows, we'll talk about the efficient influence function for this problem. And we'll talk about how to benchmark or calibrate sensitivity parameters or source data as well. And this data, we're going to do some preliminary data analysis in Pennsylvania. So where I spent 5 years of my time, a long time ago. Before I begin, disclaimers. None of us are experts in U.S. elections or voter mobilization by training. But as a data scientist or statisticians, this particular cycle of elections are very unique for a variety of reasons I'll talk about below. And actually, it helps us understand how do we use these tools to transfer across time. And the beauty of this particular set of elections is that the two candidates are identical. And again, I'll talk about this more. We also hope to bridge the gap between practice, specifically what people use, and modern statistical methodology that has been developed for the past 10 years. And all of our data analysis is preliminary. Voting data gets updated weekly, and we're still gathering data from other battleground states. So any comments and critiques are very, very encouraged throughout the talk. So the motivation for this talk comes from a 2020 digital ad campaign by Aggarwal and our co-authors. So they wanted to estimate the impact of online advertising against Donald Trump and voter turnout in 5 battleground states: Arizona, Michigan, North Carolina, Pennsylvania, and my state, Wisconsin. And so the way they did this is by a stratified randomized experiment that they ran from 2020 all the way to February 2020 to November 2020, where they stratified by gender, race, and age groups. And all these are discrete, and this will become important later. And about 1.7 million registered voters were randomized to receive about, on average, 754 ads against Donald Trump by this left-leaning nonprofit organization that funded this entire study. And the control group is that they didn't receive any ads from the acronym group. The outcome that they were interested in is whether they voted in the 2020 elections. And again, this is binary, and this will become important later down the road. And really, the fun part of all this is that in practice, most people just use linear regression, because this is not only the most simplest, but it's also the easiest to explain throughout. And so we're going to actually use the exact same approach to do this for our analysis. So what are the type of ads that the treatment group faced? There are roughly 2 ads that they were facing. One is just ad promoting news stories. So maybe there's a news article, and then these platforms are promoting it. This one in particular is kind of interesting. They were they were concerned about turning Roe v. Wade in 2020, and then it happened in 2022. So again, the similar ads could be used. And then the second ad is a traditional video campaign ad, where essentially there's like a video of some voter that may have voted for Trump in 2016, but don't want to vote in 2020. So we're just going to summarize some key results in Aggarwal et al. That's relevant to our effect. So the effect they were measuring was in difference in voter turnout between treated and control. So these are intent to treat effects and difference in probability scales. Just to give you a sense of what a negative effect means and a positive effect means, these are important for practical reasons. So a negative effect means that the ad against Donald Trump actually decreased turnout at the end of the day. So this could have happened. A mechanism that they hypothesize is that perhaps a Trump supporter may be discouraged to vote after the ads against him, negative ad against him. A positive ad, on the other hand, is an ad against Trump actually increased voter turnout in 2020. And so one mechanism that they explain could be possible for this is that a Biden supporter may be encouraged to vote after all the negative ads, about 750 negative ads against Trump during the February 2020 to November 2020. So the overall ATE turns out to be negative 0.06 percentage points. So this is very, very tiny, with a standard error of 0.12 percentage points. And as the paper quote, that we can affirm that the overall effect estimate of the ad against Trump on voter turnout is effectively 0. And so this isn't, they had some interesting discussions about this, but what we're interested in is another interesting discussion in their discussion part of the paper, which grabbed our attention and motivated this work, which is one reasonable question that they wanted to ask is how well our findings would generalize to other electoral contexts. It could be that the 2020 election was exceptional because of COVID and other idiosyncrasies of the candidates. So perhaps the digital advertising campaign that they ran in 2020 would have larger effects in more typical settings, such as not during COVID. So that is the key question we try to answer, specifically the question that they raised. Would the negative ad against Donald Trump remain ineffective in 2024? And the reason we chose 2024 out of all the other election cycles is that 2024 provides a very unique opportunity to study this question. Notably, that there are 2 same presumptive candidates from major political parties, Biden and Trump, and both candidates are actually seeking a second term. And the last time these 2 happened was in 1892, about 100 years ago, more than 100 years ago. You could imagine similar ad campaigns, which is an ad against Donald Trump or maybe even ad against Biden. And recent polls also suggest that the economy is still a major factor among voters. However, as all of us may recall, there are some big differences between 2020 and 2024. 2020, COVID-19 happened. George Floyd, death of George Floyd, racial unrest. I was 4 years younger back then. 2024 now, there's abortion, immigration in Ukraine and Israel that's happening at the end of the day. Okay. So how do we recognize the fact that there are differences between 2020 and 2024, but also at the same time learn from all this, the very expensive advertising campaign that they ran in 2020? So the way we approach this question is through transfer learning with sensitivity analysis. So essentially, we use transfer learning, or specifically domain adaptation or distributional shift, to learn from past ad campaigns in order to inform future ad campaigns. The other part is the sensitivity analysis to quantify our belief, our well-known belief that the 2020 and 2024 are actually not the same, and in doing so, provide a plausible range of additive effects that could happen in 2024 based on how similar or different 2020 and 2024 are. So some prior works in this area, specifically on methodology. The closest related literature is transportability and generalizability. We are definitely not the first ones, nor the only ones to incorporate sensitivity analysis and transfer learning or generalizability. And this is a very small list. You can dig through more, and there's hundreds, if not thousands, of papers in this area. And our goal really is to tailor these methods to address our particular question at the end. So what is our particular setup and question approach that we use? So we allow for voter demographics to shift between 2020 and 2020, for recognizing the fact that the voters in between those 2 election cycles may actually be slightly different. We also allow for the fact that the ad effect between 2020 and 2024 may actually be different. So whether you voted given an ad in 2024, which we call the target population, may be different than whether you voted given the ad in 2020, the source population. Also, we assumed that the RCT was conducted in the source, which was the case for our data, and we assumed that the source and target did not measure the exact same voter covariates at the end of the day. For example, in our RCT data, in their RCT data, they measure voters' Trump support score in groups, whereas we don't have this score as of now. And also, generally, if you have an RCT in the source population, they tend to collect more covariates based on the fact that it's an RCT, and usually that implies that the source covariates actually are bigger than the target covariates. And most of the work assume that the source covariates and the target covariates are identical. And this has implications, as we'll see in the efficient influence function down the road. Also, we heavily leverage the discreteness of the voting data. I was surprised that most voting data is very discrete, probably for privacy reasons. They don't measure age directly. They measure the range of age and various other things as well. And finally, our goal is to study the AT in the target population, which is the ad effect that would happen if in 2024 against Donald Trump. For method-wise, so we're going to use regression, probably the most popular and familiar tool for analysis, and we're going to use bootstrap because it's also very simple to do rather than sandwich estimators, which is what the paper did. We'll just tailor it for transfer learning. And actually, because of the data's discreteness, this regression estimator is actually non-parametric and efficient because the models, the outcome models don't. The other one is that if, on the other hand, this data is not discrete, we did develop an efficient influence function in this. If time permits, I'll discuss some interesting properties of this. If not, I'm happy to discuss offline as well. Another big part of our paper is in the analysis portion is how to calibrate sensitivity parameters. So there's a whole debate in this literature and what is a large or small or plausible range of sensitivity parameters. And the way we do this and the way we think is, I think, particularly useful for transfer learning where the source data is an RCT is by creating dissimilar partitions. So, and I'll explain exactly what this is. And just as a reference point, though, another popular way of actually calibrating this is excluding one covariate that's been measured, and this has been talked about since the early 2000s. There is a discussion in section 6.2 of Carlos and Chad on whether this is a good idea or not. And this is just my own tangent that may be useful for future discussion points. Actually, cross-fitting tries to create sample splitting, so to reduce observable bias, specifically overfitting bias. But actually, for sensitivity analysis, I actually started to think that dissimilar partitions of the data could help us understand observable bias in a non-parametric manner. And this is a general philosophy that's advocated by Paul Rosenbaum's whole work on evidence factors again. So before I begin, any questions?
Hi, Hyunseung. We received a question, but Xinran has been answering it.
Oh, great. So then I will continue on with some of the notations and how we set this up more formally. So just a lot of notation, but I'll walk you through one by one. The population type we denote with the variable S. S is a binary that takes 0, 1, where S is equal to 1 if it's in the source population, specifically the 2020 data, and S is equal to 0 if it's in the target population. So this is 2024 data. The outcome in our case is binary, whether you voted or not, with Y equals to 1 being that you voted. The treatment is whether a binary as well, where A equals to 1 is an ad against Donald Trump. Covariates, we partition into two types. So we consider the entire set of covariates XP, and these are the source covariates that the source covariates have. So this is RCT covariates. And the target covariates, the covariates in 2024 is a subset of the 2022 RCT covariates. The potential outcomes are as follows. Y1 is if whether you voted or not, if contrary to the fact that the voter got the negative ad. Y0 is whether you voted or not, contrary to the fact voter did not get the negative ad. And the causal estimate of interest is the linear contrast of this thing on the target population, S equals to 0. So it's helpful to look at the partial God table for this. So this table essentially illustrates what the data look like for the data scientist. So for the top row is the source RCT data where all the S's are 1 because it's from the RCT. These are the covariates that they measured. And this is their treatment indicator. By SUDVA, we get to observe one of these two combinations and the outcome, whether you voted or not. The target data, the 2024 data we have is S equals denoted S equals 1. We only get to observe a partial subset of this thing, and we don't get to observe any of this at the end of the day. Now, the goal at the end of the day is essentially identify the column mean of this thing and this thing on the second row of this table. And then to do that, we first learn the column mean of this thing in the source data and then transfer it over into here, migrate it over based on the overlap between here is essentially the idea of transfer learning. So what are the assumptions that actually enable this? So the first three are the standard ones in stratified RCTs. You have that the observed outcome is one of the versions of the treatment assignment A, observed treatment assignment A. you have a randomized treatment, and in this case, we do have a stratified randomized experiment, so this is true, and that there is overlap between treated and control groups. And again, if it's an RCT, which is the case for us, this pi x is known in advance. The other assumptions are the transportation assumptions. So once you estimate the ATE in the source population s equals to 1, how do we transport that in the target population? One is the overlap, that the covariates between the source and target are similar, have sufficient overlap to transfer. And the fact that the sample indicator does not depend on the potential outcomes given the voter demographic V that's shared between 2020 and 2024. As you can recognize, this is all written in terms of observable, so you can actually check this with the data, and I think Melody has some nice work on this as well. Well, this one, you have to take it for faith that this thing holds true. And the reason you can't check this is you don't get to observe this. And more importantly, for our context, 2024 election has not happened, so we don't actually know what the implications of this as well. There are also several hundreds of works that discuss the plausibility of these assumptions, and we refer to these works for further details. So if all these 5 assumptions are plausible, and if you believe they are true, and we believe A1 through A4 are true, but maybe A5 may not be so, you can identify the target ATE on the source target population as follows. It's essentially a law of total expectations 3 times, where the first expectation is essentially the conditional average treatment effect, so the heterogeneous treatment effect among participants X in the source population. The second expectation is essentially projection of this on the covariate space that are shared between 2020 and 2024. And the third one is to reweigh this V so that it goes from the source population into the target population. So that's the last expectation. For reference, if these 2 are the same, so that the target covariates and the source covariates are identical, these data become exact. The second step disappears. In other words, actually, when the source and target covariates differ, we actually have an additional nuisance parameter, which is essentially the projection of the Kate onto a smaller subspace. And there's a nice recent work by Zhang et al. That discusses the additional nuisance parameter that's introduced. And we'll talk about this if you have time for the influence function part at the end. However, we know that 2020 and 2024 probably are not similar. And so how do we quantify that dissimilarity between it? So suppose we assume, let's say that transportability does not hold. That essentially means that the 2024's add effect may be different than the 2020's add effect. And so to measure the deviation between these 2, we actually use the odds ratio approach. So essentially, the odds ratio approach says that the odd of voting in the target population differs from the odd of voting in the source population by an exponential of gamma A at the end of the day. And odds is just the probability of voting for a particular voter demographic in this particular population here. And essentially, this blue part is estimable in the sense that in the source data, we get to observe this and we get to estimate this. But in the target population, i.e. 2024, we don't have information on this, and we have to rely on the assumptions. A5 allows us to say that these things are equivalent, which allows us to transport. But in the case where A5 fails, we allow these things to deviate by this factor exponential gamma A. And so again, because this red part is observed, there's no way to estimate this for those who are not familiar with sensitivity analysis. And these things are gamma A is chosen to quantify the differences between the source and the target. And we'll talk about what that means and how to calibrate that, what is the plausible range of that in about 20 slides from now. In general, but though a larger gamma implies that there's a large difference between the 2020 and 2024 elections. So how to interpret this before we go to the data section is as follows, and I want to really thank Xinran for creating these wonderful slides for here. So if gamma A is equal to 0, then that means transportation assumption holds. That means that if this is 0, this exponential is 1, which means that the odds between the 2 voting in 2024 and 2020 are identical. So how does that relate to like a plot, let's say? So on the left-hand side is the source data where we get to observe some V and the voting probability. So let's say YA. And the little dashed lines here is some observations of the V, and this is your observed voting probability. And by the RCT assumptions, the A1 through A3, we can actually roughly estimate this curve. And then if gamma A equals to 0, that means these 2 odds are identical. Effectively, what this is meaning is that you just can transport at the end of the day. And just as a side note, in the target, we don't get to observe voting probability because we haven't seen it yet, but we get to observe their voter demographics, which is in this x-axis at the end. So what if gamma A is not equal to 0? So these odds are different. The odd ratio is not equal to 1. So a larger gamma, as you recall, it implies that there's a larger differences between 2020 and 2024. And it's important to actually recognize the sign of this difference just because of the nature of odds ratio. So a positive gamma means that there was more turnout in 2024 after receiving the ads against Donald Trump compared to that in 2020. And so positive gamma that actually means that there's more turnout on voting, which means the voting probability increase in this curve here. A negative gamma, on the other hand, is actually that in 2024, there was less turnout after receiving an ad against Trump compared to that in 2020, which means that the voting probability also decreased here. So you can kind of see that depending on the sign of this, the way that the probability, the transfer learning shifts in the upper direction mattered at the end of the day. And this also has implication for the actual effect size that we're going to effect estimates that we talk about later down the road. We can also do a 2-parameter sensitivity model, and it's simply just an exponential tilting of this as well. There is a whole set of remarks that I think I might not have time, but I'll just highlight a couple. This has already been known since the early 2000s. This, even though we're making a modeling assumption, it doesn't place any observable restrictions on the observable data. And the simple reason for this, although Robbins has a technical reason for this, is that we don't get to observe this whatsoever. We don't get to observe what 2024 looked like. So essentially, placing this doesn't place any observable restrictions on what the data would look like. And these are discussed in these two works here. There is a pseudo R-squared version to interpret this gamma if you prefer pseudo R-squared and with a binary outcome. You can directly use proposition 3 of Frank-et-al. To do this. If you don't like the outcome parameterized in this way, if you wanted to parameterize it this way, you could also parameterize the opposite way by Bayes' rule and by following Ray Carroll's approach and partially linear logistic regression model. You could also say, I don't want to do it on this alone. I want to depend on covariates. You could actually have covariate dependence on here. We call this a local sensitivity analysis. And if you're interested, we can discuss this more down the road. There are some works that use this model, and there are many works that don't use this model, but this is just as a small reference of those. And there is a long and very, very healthy discussion about what constitutes a good model for sensitivity analysis. If you're particularly curious this lunch, you can kind of look at this commentary back and forth where they have some interesting things to say about each other's work about sensitivity analysis at the end. Okay. So with assumptions A1 through A4, which we think we know for a fact that holds with our data, and the sensitivity model that we propose, we can identify the potential outcome on the target population as this thing here. And really, if you look at this very carefully, it's an exponential tilting of this function, the projection of the Kate onto the space of V by the exponential tilt here. And if the transportability assumption holds, that means that the 2020 and 2024 are comparable, then this all boils down to just simply this thing. That means that the denominator actually just cancels out, then you only get left with the numerator here at the end of the day. Okay. So this identification strategy actually provides a very simple plugin of estimator. I do have to admit, though, I don't usually do this because of the fact that there are nuisance parameters, that there's plugin biases that happen. But in our particular case of voting data, this is actually the simplest and also the most probably is the most efficient because the fact that the data is discrete. So if you look at this formula very carefully, the nuisance parameters are essentially this portion here. So this pulls out, and all you have to care about is the expectation of this thing as a function of V. So the projection of the Kate onto the function of V here. And as long as we estimate this well, then the rest of this is you can just plug in and then take the sample average and target population. So that's what we suggest that you do with voting data in general, is that you estimate this from the source data. One example is just regression, where you regress the weighted outcome. This is a propensity score based on V to get this target here for the treated data. And if you don't want to do this, certainly you can be very fancy about it. Because it's an RCT data in the source, you can find ways to consistently estimate this using your favorite tool of inference at your disposal. But this is, I think, by far the simplest and actually works very well. And because these are discrete, also it becomes efficient too. So then after this thing, we just take the mean of the exponential tilted version. So we take the plug-in estimate that we just literally plug in here and then just average it by the people in the target, and then take the difference between these two and get our theta estimates as a function of both the sensitivity parameter for the treated and the sensitivity parameter for the control. Again, since our voter data is discrete, this plugin estimator is non-parametric and efficient. And for a formal, this is the one time where I can cite this paper that I read in grad school. Theorem 1 of Chamberlain directly applies because this is entirely discrete data. Yeah. So In addition to just using simple estimators, in practice, if you work with collaborators, they prefer Bootstrap over Sandwich. And partly, even though I like Sandwich a lot for various reasons, Bootstrap is just convenient. And we also propose a Bootstrap way to do this. Now, if you think about transfer learning, there's an interesting concept about what is random and what is not random. But if I have time, we'll talk about it. But there's one valid Bootstrap way to do this, and which is you just resample from the target source data, you resample from the target data. And then with the resampled source and target data, you construct the AT estimator based on what we just presented. And let's say you want to construct a percentile bootstrap confidence interval here. And then if this thing is smooth enough, so the projection function of the Kate onto the set of common covariates and the Donsker conditions hold, this procedure yields a valid asymptotic 1 minus alpha confidence intervals data. And thankfully, again, because of this leveraging the voter discrete data, this thing automatically holds for everything. So you could do this and get the inference for data just by straight up bootstrap rather than sandwich, which is what the original Aggarwal paper did, actually. I think I have time for this. So there is an interesting digression that I want to talk about, maybe to come into discussion. It's actually curious to think about what sampling uncertainty is in transfer learning, because it's always thinking about a hypothetical target population, and it's not clear whether the hypothetical target population is a sample of the target population or the actual entire target population. For our case, if the target population for the voting ad is all registered voters in a state or census level data or simply fixed, then there's actually no randomness in the target data. And the only source of randomness is essentially from the RCT or the randomization of the treatment or let's say you sampled it. And then if that means that you can, for the bootstrap procedure above, you don't have to resample the target data at the end. I think there's an interesting discussion to be had about it. That's outside of this talk, but I'm happy to talk with you if you're curious about this as well. One more thing about efficiency. So you can derive the efficient influence function, and we have derived it. This efficient influence function is probably the most messiest one that I've seen in my lifetime so far. And part of the reason is because the covariates between the target and the source are not the same. And also the sensitivity analysis introducing another exponential gamma term that you have to deal with. This thing is not doubly robust when the transportability assumption is violated, and this has been discussed. A version of this has been discussed when the case the covariates between target and the source are identical. We think this is very useful if you actually have transfer learning covariates, or the covariates are same between 20 and 20 and 24 and are continuous. Some technical remarks. If you wanted to use this, you do have to estimate a lot of this thing. Really, the hardest thing to estimate is this function here. If you have continuous phi. Our EIF does recover Zhang's EIF when they assume transportability, because they do assume transportability in their setup, but they'd allow for this to be different. And also, if you're more technically curious, this EIF version does not reduce the plug-in bias from this thing. So one source of concern, if you know this literature, is that if you plug in simply the regression-based estimator, there could be biases that doesn't cancel out. Therefore, that's why I use one of the reasons of using efficient influence function-based estimators. But with when the transportability assumption holds, this plug-in bias does not go away. You still need to estimate this very fast or to achieve any asymptotic normality result. So before we go to the next part, which is the data part, any questions?
Currently, we don't have an active question.
Okay.
Thanks.
Great. So rest of the talk will be on the data. So this is the most exciting part, and especially for people who are living in Pennsylvania. So we got this data 2 weeks ago, and this gets updated every week. So it's quite expensive to purchase this every week. So we purchased it one time, April 15th, right before the OCS talk and right before Xinran's poster session on this at ACIC. So this target population is 4.8 million registered voters in Pennsylvania across all 67 counties in Pennsylvania. So the shared covariates between the RCT from 2020 and 2024 are the age group, gender, and party, and an incomplete voting history that they had. However, the RCT collected more covariates. In addition to this, they collected race and missing voting data history, which the data we purchased does not have. And so we look at each county at a time just to see whether certain counties have a different effect, a transfer learning effect or not. So the registered voters in each county range from about 1,000 roughly registered voters all the way up to 685,000. So the median county registered voter county number is about 25,000. And just so that if you never lived in Philadelphia, and UPenn is in the Philadelphia County, CMU is in Allegheny County, and Penn State in Centric County, and this will become relevant as we go in the next few slides. For sensitivity parameters, we start with this thing, and we'll talk about how to calibrate this thing and what is a plausible range of this. And for inference, much in the spirit of being applied friendly, we literally use the plug-in estimator of the bootstrap, which is theoretically correct. So when we believe that transportability holds, that is 2020 and 2024 identical given voter demographics, then the ads against Trump on turnout will be ineffective for every single county in Pennsylvania. However, if you believe 2020 and 2024 are not different, then the ads can definitely be significant under certain values of gamma 0, gamma 1 desensitivity parameters. And here's just a plot of 2 counties. We can generate this plot for 67 counties. Let's focus on the Philadelphia County where UPenn's located and the CMU County where Allegheny's located, Pittsburgh and Philadelphia. So on the x-axis is the odds ratio in terms of the gamma 0. On the y-axis is the odds ratio in terms of gamma 1. The origin here is the case where the transfer A5 holds. So in this case, in both counties, the ad effect is insignificant. And this holds for all the counties that we have looked in Pennsylvania. On the upper left is that the case where the ad effect is significant in positive direction. So this increases turnout. And that happens, let's say, as an example in Philadelphia, when if the ad against Trump raised odds of voting in 2024 by 1.5 times the same voting odds in 2020, and the odds under the ads remain the same between 2020 and 2024. So the treatment effect, the treatment potential outcome shifted by about 1.5 times, where the control potential outcomes did not shift between 2020 and 2024. And if that's the case, it represents the point here. The ad effect is positive, meaning that sending these negative ads against Trump will increase turnout in Philadelphia. And the same goes for the opposite. You can interpret it the opposite way for the negative effect. So that these ads, if you send it out, will decrease turnout in Philadelphia. And so a couple of things to notice, these boundaries between where the ad is significant in positive or negative direction differs between county to county. And to summarize this in a more compact way, we decided to look at the smallest, the absolute value of the difference that makes the ad against Trump have a significant effect on turnout. And so what do we mean by small and large here? A small exponential of this suggests that the ad is very sensitive to small deviations between 2020 and 2024 differences. And that means that essentially the ad effect, what we say about the ad effect in 2024 is very sensitive to slight changes between 2020 and 2024 elections. A large exponential suggests that the ad effect is insensitive to large differences between 2024. The other means what we say about the ad effect in 2024 will be less sensitive to changes that happen between 2020 election and 2024 election. And so on the first row is the most sensitive county. So these are sensitive to very slight changes in between 2020 and 2024. The first column is the positive ad effect. So this increases turnout. The second column is this decreases turnout. And you notice that Philadelphia and Monroe County are the most sensitive for a positive effect. That is, even slight changes in the 2020-2024 would potentially lead to increased turnout in these 2 counties. On the other hand, Bedford and Fulton is sensitive to a negative turnout, negative ad effect, so a decreased turnout. That means that even at slight changes in 2020 and 2024 would actually potentially lead to decreases in turnout at Bedford and Fulton County. On the opposite side of the spectrum is the least sensitive counties. So these are counties where they'll be least sensitive to a positive, higher turnout, and these counties are counties where it will be least sensitive to a lower turnout. One interesting thing here is that Clinton County is the least sensitive for both negative and positive ad effects between 2020 and 2024. And this will be interesting if there's a political scientist in the audience of why, because we looked at this county, it's mostly Republican leaning. The only time they turned Democrat leaning was in 2008 when Obama was elected. But it'll be curious to hear your thoughts on this particular reason. So a natural question, if you look at that table, is, what is a large and small gamma, right? It could be that gamma of 1.001 is large, or gamma 1.05 is large. And in sensitivity analysis in general, there's always a question, ever since I learned sensitivity analysis in 2012, about what is a large or what is a small, what is a plausible range of gamma at the end of the day. And there are many ways to answer this question. So we present one solution to this. I think that's particularly useful for transfer learning where the source population is an RCT. And we do this by a fairly generic approach, which is to create dissimilar partitions of the source data. So how we do this is as follows. We create 2 partitions of the source population into 2 dissimilar groups. So these 2 subpopulations are not similar with respect to what the ad effect looks like. For example, in Aggarwal, this is a source population, we created these two partitions, the blue collar states, or the blue wall, so to speak, and the not blue wall, so the not blue collar states here at the end of the day. And so we just create, because we felt that the add effect in these three states may be different from the add effect in these two states. And we use one of these partitions, synthetic partitions, I guess, as a source, and the other as the target. And then the beauty of this is that because the source had an RCT, you can actually estimate the target's ATE in two ways. One is simply using leveraging the RCT to estimate the ATE in the target population. Let's say this is the target population. And you can get the confidence interval as well. We call this the Oracle CI, similar to the gold standard that you would want to run in these two states. The other CI you could estimate and get the ATE effect is by using the transfer learning approach. We can learn from what we learned from the blue collar states and see what the effect would have looked like in these non-blue collar states. And we can estimate the ATE and its CI for different values of gamma 0 and gamma 1, and we call this the transported CI. And then the C here, the subset C, is essentially the subset of gamma, subset of these interval gamma where this interval overlaps with the ATE for the Oracle CI. And this is what we call the plausible range of the sensitivity parameter. So if the CI from here overlaps with CI from here, we look at all the gammas where the CI from here overlaps with the CI in here. Because this is the golden truth, the ground truth of the standard error. And this is what we transported because we thought they were different. And these are the plausible ranges of gamma you can think about at the end. Melody also has another idea of doing this to assess a different assumption, A4, which is the overlap condition. So how does this look like in a plot? So on the x and the y axis are saying the gamma 0 and gamma 1. And instead of significant and insignificant add effects, now we have a plausible range of add effects. And outside of this is the implausible range of add effects. So within here are the intervals where the transferred CI overlaps with the Oracle CI. And outside of here, the transfer learning CI did not overlap with the Oracle CI at the end of the day. And we'll actually then take this plausible range of C, and then we'll actually overlap with the 2024's gammas where the add effect is significant to figure out which counties actually have a plausible range of gamma that will make their add effect significant in 2024. And so that's the result here. So the before calibration, so this is before we overlap with the set C here, this is pretty much every county except Clinton County could have a significant positive add effect. However, after we restrict our gamma to the set of C where it's plausible based on our dissimilar partitions, we end up with 9 counties where the positive add effect is plausible in 2024. And these counties are sensitive towards a positive add effect in that if you deliver the ads against Trump, they would increase turnout. If you look at these counties in more detail, and if you know Pennsylvania a little bit, these are mostly urban counties, so Philadelphia, Montgomery, Pittsburgh, and Allegheny here, or in college towns, a Central County member is Penn State is. Also, interestingly enough, this set of rows here, Northampton County is called the Pivot County by Ballotopia. Biden actually only won this county by 1,233 votes out of 172,000 votes at the end of the day. And most importantly, perhaps interestingly enough, all these counties are counties where Biden won in 2020 at the election. So this perhaps suggests, based on what we take away from Aggarwal's Kate analysis, is that Biden leaners may be encouraged to vote because the ad against Trump may be effective in 2024. And this actually aligns with the Aggarwal suggestion that the AT effect may be actually more significant if you stratify by this Trump supporting score. Now we can look at the negative effect. So this decreases turnout. And so again, before calibration, before we overlap with the set C, and after we overlap with C, you notice that most counties are actually sensitive towards a negative effect. That is, the slight deviations from 2020 and 2024 could actually suggest that the ad could reduce turnout, voter turnout. Now, the most sensitive counties, the smallest gamma difference is in Fulton and Bedford County. And so I never heard of this county when the data analysis presented to me. So I looked it up. And actually, it's the counties with the largest margin for Trump voting in 2020 by far. So I think in Fulton County, 85% of voters voted for Trump, and in Bedford County, 84% voted for Trump. So this could be interpreted various ways. We're not going to interpret it beyond what we noticed. But one general interesting thing here is a lot of this election voter mobilization campaigns talk about swing counties. We thought it would be interesting to look at swing counties for ad campaigns. And these are counties that actually show up in both. And Centre County, Lehigh County, and Northampton County are sensitive in either direction. That is, slight changes in 2020 and 2024 could actually mean that the voter turnout could increase or voter turnout could decrease. So we call these swing counties for campaign ads. So some preliminary takeaways from our analysis. So if we believe 2020 and 2024 are identical after adjusting for covariates V, then all counties will have near zero effects in 2024 based on the information provided in 2020. However, if we believe that they're different, then few counties could have a positive ad effect, that is, it increases turnout, whereas most counties could have a negative ad effect as it decreases turnout. The direction of positive and negative does depend largely on the counties leaning towards Trump and Biden based on the 2020 elections. And the direction can also go in both ways and some swing counties. So the swing counties that we mentioned in the slide ago. More general takeaways, and again, this will definitely change as we analyze different states, is that a large set of we could make this thing less sensitive. I would like to thank Melody, though, for pointing out there's a case where this is not true, especially if you increase this for a variance-based sensitivity model with an AIPW estimator. This could actually hurt sensitivity analysis. But for us, we see that a large and sort of V actually is helpful for our case. Sample size does matter, but the general consensus that we're reaching right now as we're looking at more states is that having a good target covariate actually matters a lot more than how many sample size we have. So some summary of the talk. So this entire talk was motivated based on this paper and the discussion in this paper on what would the ad against Donald Trump in 2020 remain ineffective in 2024. And the way we address this question, obviously there are many ways to address this question, is by using transfer learning and sensitivity analysis. And the setup is roughly that we have a source that is RCT, and then the target population and stored population do not have the same covariates at the end. For the analysis approach, we could have went the fancy approach, and we did have one fancy approach, but we also propose a very simple plug-in estimator with a bootstrap SC confidence interval just to avoid a sandwiching part of it. And we also talk about this calibration and sensitivity analysis as a source data as well. We presented some preliminary analysis of Pennsylvania. Again, all this is preliminary. Voting data gets updated every week, and this may change as we go closer and closer to the election. Some ongoing work, we're repeating this analysis in Wisconsin, North Carolina, and Georgia. Georgia is very interesting, actually. Georgia, well, I have many things to say, but like there's like an interesting voter demographic here. And depending on which county you focus, this could have very, very interesting results. Unfortunately, anyway, I'll talk more. If there's time, I'll talk more. The other thing that we want to work on is a lot of political scientists and a lot of people who work in voter mobilization know that midterm elections matter, especially between presidential campaigns. And we want to also use this to improve data hat estimate and also to improve calibration. How we do this, we're still figuring this out, but this is something that we're working on. And a more general question I think Melody will talk about is how to calibrate sensitivity analysis, or benchmark sensitivity analysis across time, which is something that hasn't been discussed compared to across space, which is what most think people discuss. To end the talk, I want to thank several people. Xiaobin, my second-year PhD student, who's also going to be at ACIC, for actually finding this very, very, very unique data. Thank you. And actually, she also found another interesting data that you can also talk to her about for her poster, which is not related to this. Also, for the Madison seminar, student seminar participants yesterday, we actually pre-tested this slide just so that if it made sense, and especially for Stephen for finding typos, really appreciate it. For Melody, thank you for the references that we missed as well as feedback, especially on a short notice. Really appreciate that as well. An updated version of this will be at ACIC and Xinran's poster session. And again, this is all preliminary. We're not political scientists, so any comments and feedback will be really appreciated. Yeah, so thank you very much.
Thank you, Hyunseung, for the great talk. Maybe we can quickly do one or two questions. We received a bunch of them, and Xinran has answered most of them. So one question now is, how can you decide if two populations are dissimilar enough?
Yeah, fantastic question. So we initially chose based on what we thought were reasonable, but again, what we think is reasonable is maybe not be reasonable to you. And I think this choice could be better informed by people who actually know about political campaigns better. We did it based on blue-collar states and not blue-collar states, based on the 2016, where the blue wall fell, so to speak, and then that's why Donald Trump won these many candidates. And also, we thought there were definitely differences between ad effects in these 3 counties based on my experience living in these 2. And versus, I haven't lived here, but that's my, maybe there are differences there. But I think creating multiple dissimilar partitions in general can help you understand the unobservable biases. So this is just one partition that we looked at.
Thank you. Maybe quickly, another question is about the concern of cherry picking when you are singling out particular counties. Like in that case, did you consider how to adjust for post-model selection inference?
Yeah, so I think there is a concern that we could look at the significant counties and further select the significant counties. Here, I think it's more, I would say, exploratory. Certainly, I think if you wanted to, I think the bigger question, the first question we have to ask is what kind of post-selection inference problem could happen here? I need to think about that a little bit more. It could be that the effect shifts. It could be that the standard error gets larger, or it could be the distribution of it shifts. I don't know on the top of my head. One thing to note here is that the target population is technically fixed because we looked at every single registered voter 2 weeks ago. So in some sense, we may avoid some of the traditional issues. But yeah, this is a good question to explore. I think the first step to asking this question is, yeah, what matters specifically, the point estimate, standard error, or the distribution? Yeah.
Thank you so much. I think for the interest of time, we can move on to Melody's discussion.
Can everyone see?
Yeah.
Okay, perfect. Let me minimize Zoom controls so that I can see. Okay. Hi, everyone. I'm Melody. I'm currently a postdoc at Harvard, and I'm very excited to be here to discuss, I think, this very excellent work by Xinran, Jiwei, and Hyunseung. This particular paper, I think, merges 2 of my personal interests, which is transfer learning and generalizability and sensitivity analysis. So I'll try to keep it short, and I'll start off with a summary of what I thought the talk was about, and then also end with some questions. Okay, so this particular talk focuses on transfer learning. And so we're interested in these particular settings in thinking about how we can transfer or transport or generalize the information that we've learned about a specific intervention in one context to a new context. And so the estimate of interest in these sorts of settings is basically the average treatment effect in this new particular context, which is denoted by the indicator S equals 0. Okay, so I guess to be more clear, when we have S equals 1, that basically denotes that we're in a randomized control trial or perhaps a specific study. And then basically we want to know what would happen to the average treatment effect if we were to go to a new target population, maybe in a new time period. And so this particular talk focuses on considering whether the results from an experiment related to the 2020 election can be transported to the 2024 election. So I think this is very interesting. In particular, there are many dimensions of potential distribution shift that we're going to be worried about, which they talked about in the talk, right? So for example, there's different contexts between 2020 and 2024. We're now in a different time period, so things could have changed just by, the passage of time. And also the underlying demographics of voters could have changed as well, right? So maybe people have moved in and out. And so all of these could contribute to potential differences in basically this average treatment effect that we're interested in. I think a question that came up for me during the talk is, since we're interested in these people who are exposed to these ads in the first set of experiments and now may potentially be exposed to the ad again, right, in this hypothetical 2024 setting, I'm wondering if we need to be worried about things like carryover effects, like if the same person views the ad twice, like would that potentially change the estimated treatment effect? Just something to think about. Okay, so in general, when we think about transporting, transferring, or generalizing our causal effects, we rely on 2 crucial assumptions. The first is something that the authors have called transportability. It's also referred to as selection non-observables or conditional ignorability, where we basically say that given a set of pre-treatment covariates, any sort of selection effect we get from entering the experiment is going to be ignorable. And the second assumption is this positivity or overlap assumption, where basically conditional on the set of pretreatment covariates, the probability of selection into the original experiment has to be non-zero. Okay, and so these two assumptions generally allow us to identify our estimand of interest, but in practice, they can be pretty untenable, right? So the set of covariates that we tend to collect between both the experiment and our target population is often limited. We're also worried about latent confounders and also, different covariates that can't necessarily capture all the confounding effects we get from changes across time as well as context. So what the authors propose is they want to embed a sensitivity analysis into the transfer learning process. And what this allows us to do is it allows us to evaluate the possible estimates that could occur under violations of the identifying assumptions. So we can essentially relax these identifying assumptions and figure out how much we can still say about our target estimand. And so they do this with a 2-parameter sensitivity analysis. And what this does is they constrain the deviations between this odds ratio of the potential outcome. And basically, if transportability holds, then we would assume that there's no difference in this odds ratio. And I think in reading this, I had a question, which is, it seems that this gamma A is defined for a single value of the covariates V here. So I'm wondering if this means that in practice, researchers should be evaluating different values of gamma for different values of the covariate, right? So, or if there's this like additional underlying assumption that is sort of embedded here, which is we're assuming that there's a single gamma A for which basically that this ratio is constant for all covariate values. And I raised this question because I think there could be a case in which there is actually variation in this underlying parameter depending on the covariate value, especially in this particular context. And I'm wondering how researchers should think about this. So in this particular setting, you have discrete covariates, so maybe it's reasonable to posit different values of gamma, but in cases where, maybe we have these higher order interactions, that could still warrant a lot of different parameter values, and that could be difficult to track. So I'm curious how we should think about this in practice. Okay, so some other questions. I was very interested in the calibration approach. And in particular, I think the sensitivity analysis proposed here is nice, in part because of its generality. And I think what would be interesting is to think about how we can use calibration to consider different potential parameter values that map to different types of violations to this underlying transportability assumption. So currently, we're using this gamma subscript A to represent all different sources of unaccounted for distribution shifts. And in particular, the way that is currently proposed is to partition the source into two quote unquote dissimilar subpopulations. And I think this was actually raised in the questions, but from my understanding of it, this seemed to be defined as subpopulations that would not be similar after adjusting for the observed covariates. And I'm wondering if this is actually what the authors mean, because the example given is blue-collar states versus not blue-collar states. So we could imagine if we collected enough covariates, you could potentially reweight these, two different states such that they could be more or less exchangeable. But this would obviously require accounting for a very large set of covariates. When I think of dissimilar subpopulations, I sort of think of an overlap violation. So we think that there are systematic differences between the source and the target that can't be accounted for by any set of covariates. So there's like actually a fixed effect, let's say, for being in, I don't know, like North Carolina as opposed to Arizona, that we wouldn't be able to account for even if we measured all possible covariates. So I think thinking about that a little bit more precisely would be helpful for me. I'm also wondering about other settings that we could be concerned about. So for example, you have the classic omitted variable bias concerns, right? So I think actually this particular setup lends itself well to considering these sorts of concerns, right? In particular, you have a set of covariates that are measured only in the experiment, but not in the target. And you could actually leverage those to help calibrate reasonable parameter values to omitting specific confounders. I had mentioned this before, but it might be useful to think about how we can calibrate shifts across time. I particularly like the idea of thinking about the midterm elections. Maybe we can leverage that sort of data to think about what are reasonable gamma values if we have these distribution shifts across time. And I think that's particularly relevant for this particular example, right? In particular, 2020 to 2024 is a huge shift on this time dimension. Okay, and then some other discussion points. I would be curious to think about how we can evaluate slightly different transportability assumptions. In particular, a common assumption that's also used in practice in this literature is thinking about like this exchangeability of the treatment effects given these covariate X. This is arguably weaker because we don't need to make assumptions on both Y1 and Y0. And so I'm wondering how we would think about generalizing in this particular framework. How we think about generalizing this framework to this particular setting. I'd also be interested in understanding the relationship with this particular approach to alternative approaches. And this is because there's sort of this rich literature on thinking about weighted sensitivity methods, where instead of constraining these deviations between the outcomes here, we're interested in constraining deviations in the underlying weights that we might reweight the units with. And then my last point is thinking about, on the design and what we can do to recommend to researchers how to make their studies less sensitive to these, distribution shifts when we transport our causal effects. This idea that we want larger sets of covariates to make our estimate less sensitive, I think this is sort of true, right? I think what we want is ideally prognostic covariates. I think collecting more covariates doesn't necessarily help and could exacerbate sensitivity because you're essentially trying to account for more shifts in erroneous covariates. And there could be complexities with reconciliating this positivity violation with this underlying conditional ignorability assumption. So this becomes more complicated with high dimensional covariates. But I agree with the point that in the talk that basically what we want is basically better covariates tends to be more important than just increasing our sample size arbitrarily. Okay, well, that's what I have. Thank you so much. Yeah, I'm looking forward to the discussion.
Thank you, Melody and Hyunseung. Very clear, great talks. Happy to hear some discussion. We still have some time, and there were a lot of interesting questions. I don't know if you can tackle all of them, Hyunseung, but
yeah, I'll be happy to. If it's okay if I share the slide again, just to make sure. Okay.
Yeah, absolutely.
So thank you, Melody, for raising great points and also helping us actually better contextualize how our work fits into the general framework. So it is true. The first point, it's a very good question. There could be a carryover effect into 2024. And there is an interesting discussion at the Aggarwal paper actually about carryover effects, how the ad effect decays over time. We think 2020, they think 2020 and 2024 are far apart enough that this will not matter, but you are absolutely right. It is plausible. And there are also different violations of this. You could, maybe if you're exposed to 200 ads versus 800 ads, maybe that might be different. Or you could have a different ad between 2024, or maybe voters talk between each other, or maybe, as you mentioned, carryover effects. So these are all possible. I think this one is the less plausible, maybe the least of the concerns versus I think this one, in my personal opinion, the ads may actually be different. But actually, maybe this is to highlight that we actually picked these years because the two candidates are identical. One of the students in our seminar mentioned, what if you go backwards in time in 2016, but then it's Trump and Hillary, which is a different kind of ads that you could potentially imagine. And even if you go back, so this is one way to mitigate that concern, but thank you for raising it. The other one is can the sensitivity method depend on covariates? And yes, so you can do this. I think it depends on what you want to explore, specifically what direction of the deviations between 2020 and 2024 you want to explore. So for example, you could say that maybe the Democratic voters and the Republican voters are different. So you could parameterize this for the, let's say, the control group's baseline voting probability without it being exposed to ads into two different sensitivity parameters if we believe that these changes are different across these two party affiliations. We call this local sensitivity model. The only challenge, the biggest challenge here is how do you interpret this thing? Because now you have 1, 2, plus another one for A1 that you have to do, that's 4. There may be very useful ways, but I do agree that this could be very useful to actually explore different deviations essentially between 2020 and 2024 based on which direction the covariates that you're interested in. The other one I think is on the dissimilar effects and overlap. Yeah, so I do believe like there are probably ways to explore this, I think, in different ways. This is just one approach. The way we look at it, it's that the dissimilar populations are the dissimilar in terms of the ad effect, not in terms of the covariate distribution. So I think there's a subtle differences between the distribution being different, the covariate shift happening in 2020 and 2024, and whether those are the ad effects between the 2020 and 2024 are different. So what we're trying to do with our calibration or benchmarking is to calibrate the effect of the ad, whether they are different, rather than whether the voter demographics shifted or not. And that's partly because we don't assume, I guess, we allow for covariate shift between the two populations. Hopefully that answers your question, and I'm happy to hear more questions at the end.
I guess sort of like following up on that. I know the overall average treatment effect was like basically null, right? There was no real difference, but I think from what you showed with your dissimilar populations, and also thinking, I haven't checked the original study. I would imagine there's probably, we expect differential impacts for, I don't know, like Democrats versus Republicans, right? Because the ads are all anti-Trump, if I remember correctly. So is it possible that perhaps for these subgroups, they have, you know, positive or negative impacts, but the aggregated ATE is null, right? So it's like, why is specifically the overall average treatment effect actually our target and not these like subgroups?
Yeah, that's a fantastic, we want to, but we don't have the data. Like we don't know 2024's people's leanings yet. And they have that data because they actually, I guess they actually know the Trump, they have this Trump leaning score that's partitioned between 20 to 800, but we would love to do that because that's what the Aggarwal et al. Also did, but we simply don't have that particular covariate to use. Yeah.
Great. All right. Thank you both. I'll think we'll wrap this up here. And sorry, just one second. There we go. I'm sorry, I will stop your screen share. Oh, you already did it. Perfect. Okay. Great. So I just want to thank Hyunseung, Xinran, and Melody for Hyunseung and Melody, great talks, and Xinran, thank you for answering all the questions. I also don't know that I've ever seen any speaker so prepared for the discussion with the slides. So I really appreciate it. That was all very clear, and I really enjoyed that. Looking forward to seeing the poster at ACIC. Next week we have a talk from Raz Dwivedi at Cornell on integrating double robustness into causal latent factor models. So I hope you all join us for that. And that's it for today. Have a great week.